All right, friends, let's chat about problem 10.36. This problem asks us about three different ions or molecules. We are to predict the electron group geometry, molecular geometry, and ideal bond angles for these three based on what we know and what we've learned so far in these chapters, okay? So the first one is CO3 2 minus. You may recognize this from early in the semester. This is the carbonate anion. It's 2 minus charge, and it doesn't matter if we're dealing with a molecule that's neutral or an ion. We go about this molecular geometry bit the same way. We first start by writing our Lewis dot structure. It's always the first step. So we figure out how many valence electrons we've got. Each oxygen has got 6. Of course, I've got 3 copies, so that's 18. The carbon's got 4. Now it's a 2 minus charge, which means I need 2 extra electrons, okay? So I add all that up, and it looks like I've got, what, 24 valence electrons available for bonding, okay? So if I'm going to make my Lewis dot, I start with the element which is the least electronegative, and I put that at the center. I then draw bonds to the other atoms, in this case 3 oxygens, and I start thinking about whether or not I can complete octets by putting in lone pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 24, 26. So this structure, as I have it proposed right here, is not correct. And that's because it used 26 electrons. I only had 24. I need to do something about that. And of course, what I need to do is share more. So I'm going to erase these lone pairs, erase these, and make a double bond here. Okay? So now I've got 4, 10, 16, 18, 20, 22, 24 electrons in my structure. That's consistent with carbonate. That's how many I had to use, and I'm good to go. So now that I've got my Lewis dot structure complete, I can start assessing electron group geometry. The next step is always the electron group geometry. Remember, when you're assessing electron group geometry, all you need to do is figure out how many regions of electron density are there around our central atom. Lone pairs count once, bonds count once, even if it's a double or triple bond. So for this molecule, I've got 1, 2, 3 regions of electron density. Double bond only counts once. 3 regions of electron density around the central atom. Now that I now that I understand what that, or how many regions of electron density I've got, I can start to decide what the electron group geometry is. And what I've gone ahead and done here is built a little model of what this ion might look like. Notice that there's a double bond over here, but the other ones are just single bonds. You can see there's 3 regions of electron density, 1, 2, and 3 over here. Okay, the double bond only counts once. So what does that look like to you? It looks like a triangle, right? And all the atoms lie in the same plane, or all the electron regions lie in the same plane. So as a consequence, we call this what? Trigonal planar. So the electron group geometry is trigonal planar. Make sense? Hopefully so, okay? Now what about the molecular geometry? Now in this case, the molecular geometry is also trigonal planar. Whenever there are 0 lone pairs, these two are going to be the same. Okay? Makes sense, because if I look at my molecule or my ion again, triangle and a plane, trigonal planar, describes the atomic geometry, or how the atoms are arranged. And it also describes how the electron groups are arranged. They're the same. Now what are my ideal bond angles here? Well, in any trigonal planar geometry, the ideal bond angle is 120 degrees. That gets the electron groups as far apart from each other as is humanly possible. Okay, so I'm done. That's the first answer. Now the second one, SO2. Different molecule, potentially different geometry. let's think about this one. First step is always coming up with the Lewis dot structure. Now, sulfur is right below oxygen. Oxygen's got 6 valence electrons, so does this one. So that means that I've got 18 valence electrons to draw my structure with, right? So I have S bonded to O, bonded to O. Try to complete the octets and see how that works. So I have 6 additional lone pair electrons on each oxygen, right? And then the central sulfur, I'd have to put 4 more, as I have it drawn right now. Now it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So my structure, as I have it proposed, is not correct because I've used 20 and I only had 18. So what this means is I have to share some more and create a double bond. So in this case, 6, 8, 10, 12, 14, 16, 18. My structure's got 18. I have 18 to use. That's an agreement, and this would be an acceptable dot structure for SO2. Now that I've established that, I need to think about what my electron group geometry is for this particular substance, okay? Now this one's a little bit different than this one in some respects if you compare structures, but one thing that's similar, though, is how many regions of electron density I had. In this ion, I had 1, 2, 3 regions, but they were all involved in bonds. In this case, I still have 3 regions of electron density, but the regions are just a little bit different here, right? Because now I've got 2 bonding regions, and this third one is just a lone pair of electrons on the central sulfur. So I've got 2 bonds and 1 lone pair, but that still adds up to 3. I guess is kind of what I'm saying here, okay? So if I was to actually draw or create a example of what this particular molecule might look like. Oh, I got the wrong piece for that, don't I? I guess I could use this as an example. It's not the optimal piece, but I'm not going to spend time to find it. What it might look like is something like this. Okay, all the 3 groups lie in a plane with one another. They're trigonal planar electron group geometry. It's just that this one at the top is now a lone pair. There's no atom there, right? It's just a lone pair of electrons. That's represented by this green sphere, okay? So this is my lone pair up here, and then I've got my bond here and my bond here to my oxygens. This would be the sulfur in the center, okay? So I've still got my triangle in a plane. It's still trigonal planar electron group geometry. That's the same. But what's different, though, is going to be my molecular geometry, okay? So I've still got trigonal planar electron group geometry. That's considering the placement of my electron pairs, right? Still triangle on a plane. But this is my lone pair, right? If I considered just my molecular geometry, which again considers only the bonds and the atoms, you can see that the situation is different because this is the lone pair resides up here. If I'm describing the shape of the molecule, what is it? It is bent. Maybe I call that V-shaped if I want to call it V-shaped, right? V-shaped or bent. Okay, so this geometry, bent or V-shaped, is what describes the molecular geometry of SO2. Water has a similar geometry as well, okay? So, although water's got, it's a different base family, but it's also bent, okay? So, now what are going to be my ideal bond angles in this particular arrangement? Well, it's rooted in that trigonal planar family, right? Hopefully you can kind of see that, where the lone pairs are up here at the top, right? So it's kind of still rooted in this triangular shape. So as a result, the ideal bond angle between electron pairs is also 120 degrees, just like it was in that first case. Now, will it deviate from that in reality? And the answer is yes. Again, because I'm trying to stress that these lone pairs up here at the top, they tend to take up a little bit more space. So instead of being the perfect 120 degrees, what that would kind of do is pinch these a little bit closer and reduce this bond angle between the atoms and the central atom. Okay, so that bond angle would be a little bit lower than this perfect 120 degrees. But nonetheless, the perfect or ideal bond angle is 120 for this particular geometry. Okay, moving on then. The last one is CF4. We always start by doing our Lewis dot. I've got 4 copies of fluorine, which gives me 28 valence electrons to play with because each one's got 7. Carbon's got 4, so if I add those together to get my total valence electrons, I've got 32 available. Okay. Put my least electronegative element in the center, that's carbon. My fluorines generally are always peripheral or terminal atoms on the outside. And then I start completing octets. And then I'll check the validity of my structure. Okay. So the central carbon's got 4 bonds. It's got its octet. Each fluorine also has completed its octet. We've got 6, 12, 18, 24, plus 8 bonding electrons. That makes 32. So my structure is valid. Okay. Now I need to assign it electron group geometry and molecular geometry. What would this look like? Okay, if I was to actually see a molecule of CF4, well, it should look something like this. Okay, if I was to actually view this, the central carbon. And here the green dots are representative of fluorine. This is what this molecule would look like. It's got the central carbon, the central atoms in the middle, that's black. And then there's 4 green spheres around that form the base of a tetrahedron, basically. So this is the tetrahedral geometry. Okay? So the electron group geometry is tetrahedral. The molecular geometry here is also tetrahedral, because there are no lone pairs. Remember, the electron group geometry and the molecular geometry will differ only if lone pairs are present. If there are no lone pairs, these two will be the same. Okay? So you can see that by thinking about, okay, well, if one of these were replaced with a lone pair, now my molecule is a different shape, right? This would be consistent with the shape of, say, like ammonia, for instance, NH3, okay? When there's a lone pair here, and there'd be like 3 bonding pairs. But here we don't have that. We've got CF4. It's a tetrahedral shape. All of the regions of electron density around the central atom are all bonding pairs. There's 0 lone pairs present. So in such cases, electron group geometry is always the same as the molecular geometry. Now, in the tetrahedral geometry, it turns out that the ideal bond angle is 109.5 degrees. And in this particular case, the CF4, that's what the bond angle is going to be, because I've got 4 atoms on the periphery. They're exactly the same, all fluorines. Forms the perfect tetrahedral shape with these bond angles of 109.5 degrees. Okay? So this is, again, assigning electron group geometries and molecular geometries. For the electron group geometry, you just have to figure out how many regions of electron density are around the central atom. Lone pairs count as 1. Any bond counts as 1. Doesn't matter if it's a double bond or triple bond, counts as 1. Here we've got 3 regions. Here we've got 3 regions with 2 bonds and 1 lone pair. There we've got 4 regions. Each bond counts once. If you can do that and you can remember the different geometries which are outlined in Chapter 10, you can assign electron group geometries pretty easily, I think, okay? Now for molecular geometry, the key there is you have to remember that only the atoms count in describing the shape. When we talk about molecular geometry, the lone pairs, they may influence the shape, but they don't necessarily go into describing the shape, okay? So for instance, if we go from the CF4 to this case, where that bonding pair is now replaced with a lone pair, The three on the bottom, their shape is pretty similar to what it was before, the base tetrahedral geometry, except that now I've just got this lone pair here, okay? Now the lone pair doesn't count to describe the shape of the resultant molecule, but it influences the shape in that it keeps the base looking the way it does, okay? Because you still got to repel against these lone pairs and move the bonding pairs away from that, okay? So hopefully this is making sense to you at this point. There are some things that you need to be able to kind of assess and think about and understand with this Vesper bit, and there's also some things that you just kind of have to memorize. Like, for instance, the bond angles. Maybe you can kind of geometrically make sense of that. A lot of students will just memorize those. The names also do make a little bit of sense in terms of just mentally describing their shapes, but you may have to do a little bit of memorization there as well, okay? But these are all crucial key skills again, so please spend some time on this.